So welcome on this beautiful Tuesday noon in late March. I hope you're all having a great day. My name is Laura Gromes. I'm the Executive Director of USGBC Central California. We are a nonprofit organization focused on the heart of California, located here in Fresno. Our mission is to transform the way buildings and communities are designed, built, and operated. And of course, in our hot area, it's very important to look at energy and energy analysis. So we're excited to have a wonderful speaker with us today. I want to mention that we are a local organization here. We are not part of a bigger organization. And we very much appreciate all of you that are members and all of you that supported us by donating for attending today. In this digital environment, there are so many classes that are offered for free, and we certainly would like to advocate for these great solutions that are out there. That's why we're offering this for free, but we really appreciate anybody that can help support our organization so that we can continue to provide these services. So Ladan Ghobad is a wonderful expert on energy. She has a PhD and is a lead BD+C building design and construction. She's a building scientist and energy analyst and focuses on energy performance analysis in new construction and existing buildings, renovations, daylight analysis, and thermal comfort studies. I am excited to welcome her, and she's going to talk a little bit more about herself and then start with her presentation. We'll be having some time for question and answers afterwards, and we'll also be integrating some polls so that we can learn a little bit about yourself and your interest. Please feel free to introduce yourself in the chat with name and organization and where you are from. We're very interested to hear from our audience, and we very much encourage a conversation with everybody. So without further ado, Ladan, please take it from here.
Hello, everyone. My name is Ladan. I am so happy to present this presentation for you today. Thank you so much for your time. Thank you so much for joining us. I'm the founder and CEO of Enerlight Consulting. I do provide sustainable design consulting, and my focus is energy and daylight, and that's how I coined the term Enerlight. I want you to get to know you more and see what is your background and what is your profession. So I would like to answer to the poll that appears on your screen because I know that we will have a very diverse group of people. You will have time to answer to the questionnaire while I briefly talk about today's presentation. Today's topic is about building performance simulation, and the learning objectives of this presentation is for the audience to be able to describe building performance simulation and its role in reducing buildings' carbon footprint. The audience at the end of this presentation will be able to identify 6 steps towards a performance integrated design process, understand the role of building performance simulation and at each design phase, and identify tools for analysis. So if everybody had a chance to answer to the questionnaire, I would like to see the results. Laura, can you share the results with us? So we have 26% architects, 4% developers, and mostly we have energy analysts here, and also mechanical engineers, and some sustainability coordinator, and also from other professions. So I will try to speak somehow that it's digestible and understandable by all of our audience. So let me start with talking about climate change. Climate change is one of the biggest issues of our days. Burning fossil fuel for energy releases CO2 into the atmosphere, trapping heat, raising the temperature of the planet, and causing massive changes to the climate and ecosystems. Buildings are responsible for about 40% of global CO2 emissions, which is the big chunk of the pie when you look at the global CO2 emissions. The 2015 Paris Agreement's long-term temperature goal is to keep the global temperature increase well below 2 degrees centigrade above pre-industrial levels, and to pursue 1.5 degrees, because it would substantially reduce the risk and impacts of climate change. In order to get there, we have two scenarios. The first scenario is to keep the carbon budget, which is the amount of carbon we can produce, at 340 gigatons CO2. In this scenario, we have to reduce the carbon emissions by 65% by 2030, which is not very far away, and we have to target zero CO2 by 2040. If we pursue that route, we will have 67% chance of reaching 1.5 degrees centigrade global warming. In the second scenario, which is less ambitious than the first scenario, the carbon budget is 500 gigatons CO2. So we have a larger carbon budget. We allow ourselves to produce more carbons, and we have a decade, 10 years more to reach zero CO2 by 2050. But in the second scenario, we have only 50 chance to limit global warming to 1.5 degrees. In anyhow, this shows how important and how urgent it is to reduce and minimize and zero out our CO2 carbon emissions. And buildings are playing a very important in this. So it is time for architects and design teams to take an action. Architecture 2030 is a nonprofit organization that defined the 2030 challenge. This challenge is requiring architects to commit to reach carbon neutrality by 2030. And what does that mean is reducing the fossil fuel energy use in all the buildings, and then generating the remaining energy consumption and energy need of the buildings by renewable sources such as PV panels. So let's talk about what goes wrong in architectural design, architectural practice that prevents designers to reach carbon neutrality. There could be so many items and so many issues in the complex task of architectural design, like, just only focusing on the client's needs, forgetting about the future generations, ignoring life cycle analysis, and focusing only on the first cost, or just feeling disempowered. However, today, I only want to focus on design process. The design process that does not include building performance analysis. So what is building performance analysis and simulation, basically? It is a set of computer-generated calculations that help designers compare design options and predict anticipated energy consumption of a building and its systems. It increases the ability to make informed decisions to improve energy performance and increase thermal and visual comfort, among all other design issues. Now, let's look at an integrated design approach where the building performance simulation and analysis takes place along with the design phases, starting from conceptual design until schematic design, design development, construction administration, occupancy. So this is an integrated approach where building performance simulation and analysis takes place at each phase. When we start at early stages of design, we most of the time do some single aspect simulations. And as the design gets more evolved, we perform whole building energy modeling. The whole building energy modeling could be started like a shoebox model, a simple, very simple box model. It can start at very early stages of schematic design. So let's see what happens at each of these phases. Early investigation means setting goals, setting energy reduction goals, understanding the local energy codes, realizing what are the requirements, finding out about any possible incentives that you have locally. And also doing environmental analysis like climate and site analysis, massing and orientation, natural ventilation, solar shading, daylight glare, envelope facade. At the schematic design, mostly when we start to think about the massing and the geometry and the design is getting some solid nature, we start to estimate buildings EUI, which is energy use intensity, the total energy consumption of the building per year, per square foot. Compare the building performance into a national median or lead baseline or a load code compliant building. And also we need to have some understanding of possible PV generation on site and estimate how much PV is required to reach ZNE and how much should we outsource and use off-site renewable energy generation. The next step is energy efficiency measures. Proposing strategies to reduce energy consumption, evaluate all those strategies, looking at them parametrically and finding their implications on the energy consumption and operational costs. The next step is ensuring comfort, thermal comfort and visual comfort, to make sure that all the design strategies that we pursued, all the energy reduction measures that we took did not compromise comfort. Extending the simulation, getting all those details about the building systems into the whole building model is the next phase, creating as designed energy performance. And also measurement and verification. So we want to continue that until the building is occupied. So doing measurements, getting data from the building to make sure that the building is performing as it was designed, and comparing the actual numbers to the predicted numbers that we had before. However, in a typical design practice, this is what is happening. Rather than the integrated process, we do some kind of early investigation, early stage simulations, which are mostly done by the architect. We forget about building performance. We never talk about that with the design team. And then we realize that we need a compliance modeling, mostly for lead or for code compliance at the very later design phases. Towards design development or construction documents. That is where the mechanical engineer or energy analyst gets involved. All the drawings are sent to him or her, and he or she is asked to create an energy model. But we shouldn't forget that compliance modeling is not supposed to be predictive, is not supposed to be precise, to provide feedback for the designer. It is just showing that a minimum level of performance is achieved. So what's the problem with that? The problem with the typical practice is that we create a whole building energy model very late at the design phase, when it is too late to provide enough feedback, when it is too late to guide the design team. So as you see in this graph, the yellow line shows effectiveness, the blue line, the dark blue, shows cost. So at the beginning, we have high impact, low cost decisions. Making changes are easy. They don't cost much. However, at the later design phases, after design development and construction documents, any single change that you want to make is costly. You have to change all the drawings. You have to make coordination with all the disciplines, and it's super costly. So it's too late to make any changes. So this practice means missed serious opportunities to reduce first costs, reduce operational costs, and reduce environmental impacts. Now I want to talk about analysis tools. The tools I am presenting, I'm not presenting all of them, most of them, are early stage analysis tools and whole building energy modeling tools. So let's get started. Target Finder is very easy to use. It's very simple. It just needs to know where the location of the building and what's the type of the building. Then it will generate the EUI, energy use intensity, of a median commercial building in the US. So it will show you what is the EUI in a median building, the similar building with similar functionality of your building. So it is very good to set a target for the design. Zero tool is created by Architecture 2030. It is very similar to Target Finder. The only difference is it's global, so it's not limited to the US. It has an expanded use types. There are different building use types that are introduced in the tool, and it's not controlled by the federal government. You need the same information, just the zip code and the building type and size of the building. The next one is Sapphira. So Sapphira is a web-based, real-time early design analysis tool that integrates best with SketchUp, although it works with other software packages. It's very useful to look at different alternatives like the impact of orientation, facade, window-to-wall ratio, shading, on the design. Daylighting analysis is simple, and Sapphira systems allows you to pick some mechanical systems as well. Insight 360 is a cloud-based application for Revit, and it's free for Revit users. It is most useful for finding buildings' approximate EUI, and looking at the impact of orientation, facade, window construction types, window-to-wall ratio, and shading. The users have a list of options to pick from, so you should pick the options very wisely to have an approximately accurate result. Daylighting is not very highly accurate because it's with DO2 engine, but for doing more complicated, more advanced lighting, it is, you can do it with LAR, which is lighting analysis for Revit, which could be very costly. The next one is Cove Tool. Cove Tool is again web-based, real-time. It works with Rhino, Revit, SketchUp. It has a wider range of performance analysis. It has target setting, load profile analysis, daylighting. It also has views, water analysis, which is not happening in the other ones, and also energy analysis. They also have added a COVID design, based on the distance, having the 6 feet apart distance, kind of cool, neat thing that is useful too. Ladybug Honeybee tools are my personal favorite tool for doing early stage analysis. And the reason for that is its flexibility and the possibility for the user to adjust maneuver and change the parameters and see what is actually going on in the program. So it comes in the format of some Rhino plugins. The tool is also developed for Dynamo, for Revit, but it was first originally created for Grasshopper and Rhino. It uses two very strong, powerful engines, Radiance for daylighting, Energy Plus for energy modeling. And it is capable of doing many, many different kind of environmental analysis, and it is free. Energy Plus is the DOE's fundamental energy simulation tool that has been funded, and it continues to get funding for development of capabilities. Energy Plus is not very user-friendly, and it has originally been used by researchers. But an increasing number of programs are developing interfaces to the E+ engine. One of the examples is Design Builder. So it's a very user-friendly modeling environment that uses Energy Plus engine. It also does daylighting simulation with Radiance. It creates the lead baseline model. It does cost analysis, optimization, CFD, and scripting. And the price depends on the number and the type of modules that you purchase. ISVE is very, it's relatively similar to Design Builder in terms of its function. So it does provide very advanced whole building energy modeling. It uses its own built-in engine, Apache, for energy modeling, and Radiance for daylighting. It also creates the baseline model, Title 24 compliance, which Design Builder doesn't do. It also has cost analysis, CFD, and scripting. And it is relatively pricey, and the price depends on the modules that you want to use. So now I would like to have a brain break and ask you some questions. I want to know if you have used any of the tools that we discussed, and a little more tools that I didn't elaborate on here. But I want to see if you have used these and if any of these tools have worked well for you. So please respond to the poll. And I also, so we have 3 questions here. So that's the first one. The second question is, do you use any other tools for building performance analysis? And if so, just let me know, what are the other tools that you use and you're happy with and you're satisfied with? And the next question is, do you support the integrated design process? Strongly agree, somewhat disagree, strongly disagree. And if you want to provide more explanation and elaboration, just please use the chat box, because I really want to know what you think about this integrated design approach. And I wanted to have an open-ended question to know what you think is an impediment for reaching that integrated design approach. But I would like to read the chat box later once you all responded to the question. Laura, do you think that we can read the results, or are we still getting more answers?
17 people answered so far. So we'll give people another chance to.
Oh, you're muted, Laura.
We'll give people just a little bit time. There's a couple of people that are still working on it. So Let's give it another minute.
Yes, of course. Yeah.
And somebody mentioned in the chat that you forgot ISVE, but there were only a certain amount of potential answers, so that was the last one on the list, so that didn't fit in. So if you use that, please share in the chat.
Oh, in the poll? Oh, I got it. Sorry about that.
Oh, no problem. The limits of technology. All right. If you have not finished it, go ahead and finish so we can launch and get an idea how many people use which tools.
So in the meantime, while people are responding, I can talk about the upcoming event. The AIA California Code is hosting a roundtable about tools and technologies. I will be moderating that session, and I'm preparing a survey and trying to, plan for that upcoming event in May. So stay tuned.
And we'll share more information in a follow-up to this webinar. Okay, it seems like everybody that wanted to participate participated. So here we go with the results.
Okay, interesting. So we have everybody used many of these tools. It's good to see that people have used them. Energy Plus and eQuest are the winners, although IES was not included, I'm sorry. But I'm sure that some people, a percentage of people are using IES. And interesting, Inside 360, I think because of using Revit and because it is provided in Revit, most people are using that. And wonderful. So we don't have anybody to disagree with the integrated process. Okay, so let's continue with case studies. So now I would like to bring some examples for each of the phases of that integrated process that I discussed, and talk to you more about real examples. The first case study is Wilson School. This is an unusual state-of-the-art public school in Arlington, Virginia. It was designed by Bjorka Ingalls Group, the big, and MEP and energy, mechanical, electrical, plumbing, and energy services were provided by Interface Engineering, the company that I used to work for while I was involved in the project. And this building is very different from any typical public school building you have seen. This is a building with 165,000 square foot, 775 students are in the school, and it was built in 2019. So the building is designed as a stack of 5 rectangular floor plates that rotate around a fixed pivot point. Each of these rectangles has a double loaded classroom floor plan, or they include a common space, such as a library, cafeteria, gym, auditorium. The building has some green terraces that are designed above each floor to provide different scales of activities, outdoor activities, from large gatherings to class-size discussions and quiet study areas. So the very first stage of the design was massing study, and the architect was thinking about all different massing options that could, possibly be created. And they wanted to know what are the energy consumption impact of different, massing options. So what I did was to summarize and categorize the different, many options that they gave to me into 16 categories. Create some, prototypes and some simple configurations to represent a group of the options that they presented me. So the criteria that I had for creating all these options was to keep the area at 200,000 square foot. So what I did was to create an energy model for each of these 16 options and to understand what are the heat gains and heat losses for each of these options. As you see here, different configurations have different heat losses and heat gains. The other aspect that I looked at was the energy consumption. So the heating, cooling, and lighting energy, those only looking at those three categories and saying which options are using less energy. So the most efficient design was a simple square building and simple rectangular building. Neither the architect nor the client were interested in those simple options. They just wanted to build something unique and amazing. So the third option was the stepped rectangular floor plates towards south and towards southeast. And that was the beginning of the time that they started thinking about those stack of buildings. At the same time, I was looking at the annual profile to see when heating and cooling energy is consumed. And I was, I also paid attention to summer closure of the school. So in summertime, the building is not occupied, and so it doesn't have a lot of cooling energy. And just thinking about how the loads look like at every single day in a year. The architect was looking in parallel, was looking at the implication of the site and try to understand how the site has an impact on the design. So this is Wilson Boulevard, which is the main boulevard, the main entrance to the building. If the building is located at the back of the site, they would have an open space for the student to have, more open area to enjoy. If the building was located on the Wilson Boulevard, they would have more enclosed space, quieter space, more enclosure. What I provided for them was shading analysis to look at three time steps: summer solstice, equinox, and winter solstice. So I looked at 9 a.m., 11 a.m., 1 p.m., 3 p.m., and the school operation is mostly in the morning. So what the shading analysis showed was that when the site was mostly shaded by the neighboring buildings because they had two tall buildings in the south and one on the east that was casting shade during the morning hours, which is when the kids are mostly in the school. The other part was orientation study. So trying to rotate the building by 30 degrees and finding out how much is the energy consumption. If you look at this graph, you might say there is less implications and less influence on the total EUI. But if we zoom out, we would say there is about 1 AUI difference when we have the building in the optimized position, which is north-south to east-west. And even 1 EUI is very important for us in those high-performance buildings because we don't have, we don't have such a high EUI. It's just 18 EUI. So even capturing 1 EUI is important to us. In more complicated shapes like L shape or just bars and other forms, it's not straightforward, but it is, and it is important to just model them, simulate them, and see what are the implications. So after many discussions with the design team and the architect, the school board, and the community, the parents, and
Mm-hmm.
all the involved people in making decisions, the architect decided to have the fan shape model, and they asked me to find out if it is more beneficial in terms of energy reduction to have the building on the south or on the north side of the site. So as you see here, this is when the building is located on the north part of the site facing south direction, benefiting from the, because of the special configuration that it has and having exposure to the south using daylight and using the, the south exposure and avoiding the shade that I presented before from the neighboring buildings. So that would save another EUI. Parametric analysis was constantly happening. It was an ongoing process, just thinking about the walls and roofs R values and making recommendations based on the amount of energy saving that we have, and also at the same time looking at the cost of each inch of insulation that we add to the walls and to the roof compared to the energy consumption, energy reduction that we have. Also, window to wall ratio parametric analysis. So this graph shows how window to wall ratio increase as you see in the horizontal axis. So this shows 20%, 30% of window to wall ratio, and the vertical axis shows the total energy consumption. As you can feel, it's a common sense, as you increase the window to wall ratio, you will have more energy consumption in the building. But the other parameter that I looked at was using different glazing types. So now each line is plotted for different glazing type that was used in the building. And the takeaway from this slide is, if you want to have more window to wall ratio, which is interesting to all architects, you have to pick a higher performing glass, and this type of graph would help the architect to choose and pick the glazing type based on the amount of saving that they want to reach. This slide also shows looking at different glass types again for each of these orientation, because of the complexity of the building configuration. The design has many different orientations, and I looked at different glazing types for each of them to find which glazing type is more appropriate for each orientation. So the design target for this building was 23.6, and we found it very early at the design phase, very early, by just looking at the Energy Star 100 score, elementary schools in Arlington, Virginia. So we plotted the average school, ASHRAE 90.1 school, and we had the design target of about 23 EUIs. And during the design process, with all the energy reduction strategies, we try to reduce the energy consumption by implementing a different strategy, and also by creating on-site solar. We proposed to reach zero net energy for this building. The second example is DGSO Street building. So this is an office building located in downtown Sacramento, designed by ZGF and Lionakis. MEP and energy was provided by Glomac, the firm that I was working for while I was involved in this project. So this is an 11-story building, 372,000 square foot, and it has very stringent goals. Zero net energy, LEED version 4 platinum certification, and maximum EUI of 25 kBTU per square foot per year. With an integrated design process and by incorporating incremental improvements to a very sophisticated energy model, we were able to achieve those goals and exceed those goals. So at the end of design, the EUI was 24.8 kBTU per square foot per year. Source EUI was 75.6, and we could reach the maximum 18 point for LEED. And ZNE was also pursued by using Smart Solar Shares program. This is a program offered by our local SMUD, which is our utility company in Sacramento, and it offers the Solar Shares program where building owners become in a contract, and SMUD provides them clear electricity that is generated by neighboring solar farms in the area. So now I would like to talk about the initiatives taken at each of these phases throughout the design. So starting from early investigation, the team started some sustainability charrettes, some workshops with all the team members and the owner. The important tasks to do was to set goals. And as I said, this building had a target EUI of 25. And learning about the local code, which is Title 24 for us here in California, and finding out possible incentives. And some of these incentives programs need a certain level of performance. So knowing that level of performance and putting that as a goal and pursuing it to be possible to use those incentives. Early investigation, as I said, climate, massing, orientation, natural ventilation, solar shading, daylight availability, and glare. The second part is evaluation and comparison. So this is when we create a whole building energy model, a very simplified whole building energy model, just to know what is the EUI of the proposed design. And in this building, by early analysis, thinking about the EUI very early stage, we understood that the building needs to be 34% more efficient than Title 24. And our California Title 24 is pretty stringent. So being to have 34% more energy efficiency than that, we knew at the beginning that this is going to be a really tough task to do. The other part of the evaluation and comparison stage is thinking about generation, how much generation you could have on the site and how much you need to outsource. For example, for this 11-story office building, there was no way to generate all the energy need from on-site PV because the roof is not enough to generate the whole energy consumption. So that's why we outsourced to Smart Solar Share program. The third step is energy efficiency strategies. And in this project, the energy efficiency strategies were having a highly efficient building envelope, using external shading, using daylighting, using daylight and occupancy sensors, very efficient LED lights, radiant heating and cooling, water source heat pump, using demand control ventilation, and having low flow plumbing fixtures, and having a dedicated outside air system with heat recovery. So these were the energy efficiency strategies. At this step, when the design is getting further developed, I created an energy efficiency measures list so that multiple design options were created, analyzed, compared, and contrasted against each other. So this type of EEM analysis allows optimization of the design via comparison while managing construction costs. So in front of each of these simulation iterations, energy savings, operational cost savings, first cost, potential incentives, simple payback, PUI, and CO2 emissions were presented when were calculated. So having all that information for each single iteration to allow the owner and the design team compare these options and choose a bundle of the most, the options that make sense mostly for the whole design team, were really important and crucial. The fourth step, ensure comfort, thermal comfort first. So here is when we get to design development, the spaces are getting shaped and figured out. And some of the spaces that were concerning for the design team, we did thermal comfort analysis to see how the operative temperature, which is the average of mean air temperature and mean radiant temperature, how that changes during the time, how occupancy plays a role in that, and if the occupants doing a certain task in the spaces feel comfortable. Also visual comfort, making sure that glare is addressed and is minimized in all the spaces. The next step, extending the simulation, getting more details to the energy model, adding all the building systems, all the details, and creating an energy model that includes all that information. This is what I call the roadmap to energy efficiency. It shows how we started from the lead baseline to Title 24 and, all different stages of design. And as, these different chunks of each energy use type has changed, we just try to make sure that the target of less than 25 EUI was pursued during the design, and it wasn't an easy task. The next step, measurement and verification. What we can do during the design is to create a plan, a measurement and verification plan to specify type, location, and quantity of meters to collect enough data to prove that the building operates as designed. So saying how many meters, where should they be located, and what kind of meters, where and how much we need to be able to measure the building and compare it with the energy model when the building is occupied. So this is the last slide that I would like to dedicate to the lessons learned. From all the projects that I have been involved in, there were some common characteristics in the most successful design project teams. The first one is team commitment. Commitment to a certain performance level. Either it is a certain EUI level or ZNE or a LEED certification level. Just make a commitment to a performance level and carry it along until the later design phases. Collaboration and communication is key. inviting all the experts, including the building performance specialists, energy analysts, to the table at the very early stages of design, listening to them, making the energy analyst an integral part of the design team is very important. The next one is championship. Having champions at every design discipline, even mechanical, electrical, even landscape design, that really care about climate change, really care about environmental impact. That was also another crucial factor to reach these great outcomes, which are, high performance buildings that look good, feel good to be within, and have minimal impact on the environment. And now I would like to, have question and answers and see if there are any questions that you have. So I would like to ask Laura to let me know if there are any questions.
Thank you so much, Ladan, for a great presentation. Yeah, if you have a question, feel free to use the chat or unmute yourself and just speak up. And while we're waiting, there's a couple of questions in the chat. Why should we continue to use eQuest, which is a 20-year-old program with many deficiencies like modeling of humidity or internal radiation?
We don't have to use eQuest. I know that I do not use eQuest. I know that some people use eQuest because it's just easy to use, but that's a true statement. The engine that is used in eQuest is DOE2, which is the grandfather of Energy+. And although it is outdated, but I know that many consulting firms still use eQuest for energy modeling. I think it's just the fact that it's easy to use.
This is Greg. I've got a question.
Go ahead, Greg.
First of all, great presentation. You did a great job kind of summarizing the approach and then showing it with the case studies. So really appreciate the studies and how you shared them. I guess my question is about what the cost of doing studies like this, or not this exactly, but I think you bring up a good point in the beginning that energy modeling isn't done enough on projects. And I think part of it is just, owners or architects or, the people that are kind of onboarding modelers early on in a project don't have a firm grasp of how much to budget for that. Can you speak to that a little bit from your perspective?
I agree with you. And I think the only one of the reasons that we don't see this kind of analysis on all the projects is because the architect and the owner is concerned about the cost. But I believe that it's again one of those issues, thinking about the first cost rather than whole life cycle analysis. The benefits of doing this kind of simulation and analysis at the early stages of design and throughout the design, the benefits and outcomes are a lot more important when we look at the life cycle of the building. So I think architects and design teams have to come up with some sort of discussions to make the clients think about those savings along the building life. And I know that there is a paper by Annika from HOK. She has studied the payback of energy modeling, and her published paper proves that among all the projects that they had, the payback period for energy modeling was very insignificant, was very small. I can share that paper. It's a really good paper. It's very promising.
Wonderful. And we can send that in the follow-up if you can provide that to me. Here's another question. How, and I think this is in regards to the first example that you show, how did the design team ensure daylight equity in all classrooms, considering that each facade was rotated and there's no shading that I saw?
There were some shading and there were more accurate daylighting analysis along the design. In that project, I was mostly involved in the very early stages, and the graphs that I showed with you and the building was before adding those shades. So it was very early, but it was addressed and they added shades, and it's the design evolved into with more details. The slides that I presented was very early stages, but very accurate daylighting analysis was performed at the later stages.
Okay, wonderful. Other questions? Please unmute yourself. I don't hear anybody. There's a question in the chat. Can you please suggest us if there's any gap right now or any possible further research?
I guess the gap is the gap in the design process. I think it refers back to the slide where I showed the integrative design process rather than the typical design process. Still there is a gap, and I see that most of the analysis is happening by the architect at the very early stages, and then they forget everything, and then they do whole building modeling, which is mostly lead modeling, at the very end stages. So I think these two should come together. And even our tools are not good at providing a wide range of, early stage as well as, whole building energy modeling. Some of the tools are really good at towards the end. Some of the tools are really good towards the beginning. We still don't have a tool that, encompasses all this, the whole design phases.
All right, wonderful. One more chance for a question. I get a lot of thank yous. People really loved your presentation. So thank you so much, Ladan, for sharing your work and providing so much insight. We'll be following up with the recording and the slides and a couple of suggestions from Ladan for further information. So thank you so much for joining us today. And if you are so inclined, become a member, support our organization so that we can host many more great presentations. And I hope you all enjoyed it, and see you next time. Thank you so much.
Thank you. Have a great day.